real quick. First up, we have Rebecca Ghent, who will be talking about diviner observations of dust and regolith.
Okay, thanks everybody. So I was asked to talk about the diviner observations of dust and regolith, and despite the title, I'm not going to talk about dust. I noticed that Ben Greenhagen was on, and I will just say that I know that Ben and some other diviner team members were involved in an effort to see if diviner could make any limb observations of dust. And if you have questions about that, I'd encourage you to put a question to Ben, maybe in the Q&A. Sorry, Ben, I've put you on the spot. So I'm sure some of you have seen this animated GIF that's been going around for 10 years of a dog digging up the regolith on the moon. And that's kind of a cute presaging of what I'm going to talk about, which is active surface processes that diviner has had an opportunity to observe. So next slide, please. This talk is very short to try to summarize all of the many contributions that diviner has made to our understanding of the regolith. It's been orbiting on LRO for more than 10 years and providing extremely high quality observations, and we have just tons and tons of very rich data. It's a very rich data set. And the observations that diviner has made have been instrumental in providing new insights into almost every aspect of our understanding of the regolith, including composition, physical properties, and how it evolves. So I'm going to focus on one very specific aspect of that myriad of results, which is the link between specifically the nighttime temperatures and the evolution of the regolith. Next slide, please. So nearly 10 years ago, Josh Banfield created a very insightful data product using diviner nighttime temperatures, exploiting the fact that the nighttime radiances that are emitted from the surface of the moon are basically almost completely influenced by the physical properties of the materials radiating. So at nighttime, you remove the influence of albedo and the changes in the solar incidence, and what you're left with is a radiance that comes from the materials depending on how much thermal energy they retain during the night. And this sets up a very profound difference between the effective temperatures or the brightness temperatures that we observe from indurated materials like rocks and finer, less indurated materials like regolith. And so Josh, in 2011, broke the physical components observable by diviner down into a simple binary mixture of fine materials representing regolith and indurated materials representing rocks, and was able to calculate two extremely important and useful data products, one of which is the rock abundance, which is shown on the left here, which is, I'm sure most of you have seen this data set before, but each pixel is given a value which represents the fractional coverage, the areal fractional coverage of that pixel by rocks or materials that radiate all the way through the night as though they were rocks. And removing the influence of those rocks, he also calculated the temperature of the other fraction, which is the regolith temperature. And so shown here on the right is a map of the regolith temperature relative to the longitudinal average at each latitude. And so it's a relative measurement scaled here from 10 Kelvin below that average to 20 Kelvin above that average. So we notice a couple of important things. On the next slide, you can see some obvious examples of variations across the moon in each of these indices. So, clearly large, young crater ejecta show many rocks, and so you can see those elevated rock abundances associated here with Aristarchus and Copernicus and Tycho. And you can also very clearly see the Maria, which show lots of small rocks because of the fact that the regolith is much thinner in the Maria than in the highlands. And those things have been studied, and many important and surprising implications have emerged from studying those things. On the other hand, when those rocks are removed and we look at the regolith temperature, to first order, the regolith is relatively uniform. And so that's in itself an interesting result, because we can see that down to the thermal skin depth, the diurnal thermal skin depth, or round numbers about a meter across the moon, there isn't much variation from place to place in the regolith temperature. So of course, the variations from that general rule of thumb are where we make advances. So on the next slide, we can see the result of some later work in which that regolith temperature has been further analyzed to produce something that we call the H parameter. So on the Diviner team, we have a thermal model, a one-dimensional thermal model that helps us predict both the surface temperatures across the moon, which we can then match to the Diviner observations, and also the temperature profile with depth. And the most appropriate model for the structure of the regolith that goes into that model is a density of the regolith that varies in an exponential way. And the H parameter gives the scale of that exponential variation. And so the result here is this map that you can see on the left, which shows it is a very rich source of information about the physical properties of the regolith. So now on the next slide, I'll talk about one very interesting and unique implication or application of this information. So Josh and some other people on the Diviner team, looking at the regolith temperature map, very quickly discovered a whole bunch of these very, very cold spots, which are associated with very small young craters that have extremely outsized thermal signatures. So craters on the order of 10 to a couple of tens of meters produce hundreds to thousands of meters of thermal influence. And on the next slide, please. Yep. Pierre Williams and some other people have further investigated these features and found that they represent a very important time marker in the evolution of the lunar surface. So they found, several thousand of these cold spots shown in the upper left from a paper by Pierre Williams in 2018. And the conclusion here is that they represent a ubiquitous and very transient phenomenon. So they fade on the order of 100,000 to 1 million years. So the important upshot here is that cold spots are regolith evolution happening in real time that we can watch right now. And just as a precursor to what Emerson Spirer, I'm sure, will discuss in a few talks, cold spots are not the only real-time phenomenon that's occurring on the surface of the moon, but I think all these things are related, and that's an active area of research. So next slide, please. So what some other people, such as Emily Costello, has done with these data is to revive some old Apollo-era modeling by Don Galt to study the process of regolith overturn. And these new observations from Diviner, these cold spots and other observations, have provided really important constraints on these models. And the upshot of all of these models is that secondary craters are the major driver of regolith overturn. You can't match the observation of the fading rates of cold spots or rays or any number of other constraints without accounting for secondary cratering. So on the final slide, the next slide, I'll just say that this is just a very small sampling of what the Diviner thermal observations, specifically from nighttime temperatures, have done, which is provide a new way to investigate this fundamental question, which is what are the details of the processes by which impacts create and continually shape the lunar regolith. So it's a canonical fact that we all accept that impacts create and evolve the regolith, and the details of that process are surprisingly obscure. And so I will just leave us with this point that I'm advocating here, which is that we need to keep watching the active lunar surface. So in terms of future directions for exploration, I think this is one of the most important things we can do, is keep monitoring these current processes. And that's all. Thanks.
Okay, thanks, Rebecca.